Yeah, hello guys. Hoping so you guys are doing good today. So we'll start with the second lecture today. So first of all, let's start with understanding how does the frame or a building works when the force is acting. That is lateral force. So usually what happens, is a earthquake load is a lateral force that is acting, and this is a lateral force acting, and this is a frame structure, and this sways, obviously, right? This will sway. And due to the sway, there is a load, that is W or mass, and this is a swaying, it will sway, and there is a length in here. I mean, this whole thing length, and there is a sway, and due to that, there is some kind of a resistance force from this side. That is correct. That is base shear. When the force is acting, so F is equal to ma. When the force is acting, there is a mass and there is acceleration happening. That is inertia force. This inertia force is happening due to this mass. There's some kind of a mass in here, and that mass, the W, where it comes from, live load, dead load, and even to the roof there is a load. Okay, there's some one clause to that, so I'll be explaining that in a while. So what happens? There is a load acting. Now understand what is this. This is a sudden movement that is happening. That is sudden movement that is acting on this frame. So this is how it is going to work. And usually what happens once the mass is defined, we need to define a diaphragm where what happens, how the load will distribute. Correct. How will the load distribute? From here, there is some kind of a lumped mass that needs to be distributed to the bottom, because ultimately the load will distribute to the bottom itself. Nothing is going to carry. These columns will carry and it transfer to the bottom itself. So how is it going to transfer? It is going to transfer to diaphragm. So I'll be explaining you guys how it works or what are the things going on. So hoping so you guys have understood the basics right now. I mean, what is the process? The load will be acting and there is a mass in here, and due to the mass, the load will be, a load will be taken from the mass and the load will be distributed to the diaphragm. So we need to define mass, then we need to define the diaphragm. So once this is done, we get the whole structure. Okay. But there are two things that we guys need to remember. Base shear and overturning force. Overturning action or overturning moment. Yeah. What normally happens with overturning moment is, imagine a frame, imagine a frame, and same way, again the sway will happen due to the load and there will be moment formed. Correct. There will be moment M1 and M2. And due to this force, keep this to be L length. Now imagine there is a force acting, and due to that there is a tension in here and there is a compression. Correct. Now what really happens? Axial tension, that is tension into length, or compression and length, plus M1 plus M2. This is the overturning force. How will it overturn? I mean, when the load is acting, how will it react? And due to that, this is a failure, and this is a different failure. That's it. Base phase shear failure and overturning moment. Base shear, how normally it is calculated is by, imagine this is, uh, height is around h3, and this is around h2, and this is h1, and force is F1, and this is F2 and F3. So if you want to find base shear, that is F1 plus F2 plus F3. This is how we should do it. And if you want to find overturning moment, we should do something like this. F1 into H 1 plus F2 into H2 plus F3 into H3. This is how you guys have to do it. So this is what it is. Base shear and moment. That is overturning moment. So now you guys have understood the basics, how it works. Let's start with how to find this base shear. There are different methods to find it. Now we'll start with that. Okay. So at first, you guys need to understand there are different ways to find the earthquake load. That is VP lateral force. Now, equivalent static method. Equivalent static method is that method that we are going to do it today. I'm going to explain that out. This is the equivalent static method. This is the formula. And dynamic analysis method, there are three methods: response vector method, model time history method, and time history method. I'll be explaining that in the future classes. So this is how it is. And first of all, I have mentioned in here that natural period TA should be less than 0.4 seconds. Only then we can follow this equivalent static method. What does that mean is there is something called as oscillation. See, there is TA in here, there is TA in here, and even here. What does it mean? TA is the oscillation, natural oscillation. So you first, before solving the problem, we need to find whether it is whether we need to follow equivalent static method or whether we should follow the dynamic analysis method. So for that, we need to first find out the T. Now, first need to understand, you should know that what kind of a object, building are you going to construct? Is it MRF building, that is without masonry infills, or is it RC structural walls, or buildings with RC structural walls? That is for different thing. When if you are providing a shear wall, uh, in that case we are going to use this. The load, some of the load will be distributed to this. How much load the shear wall will take, that depends on that, and the all other buildings. So imagine you have a building where you have provided all the infills, that is walls, the stones you have provided, all those things, and in that sense we are going to use this method. So let's take an example right now in our case. So TA to be 0.09 into what is H and D. So what really matters in here is, see, if there is no infill, so we don't have to consider T, that is depth, breadth of the building. Why? Because normally if you're going to, if there is a weight, if it's a weight acting, if there is object and the weight is acting in this format, what do you think? The sway will be kind of less, and even this area doesn't matter. The base won't matter, and the base width won't matter. But when if there is no infills, so that doesn't matter. But if there is an infill acting on this, the base matters because load will decrease, the TA time period will decrease. So right now in that case, right now because we are using this method, we are going to follow this. And there are different kinds of buildings. Maybe a building will be like this, or maybe there is a filling in here and the filling will be different. And maybe the building is like this kind of a shape, or the building may be vertically. It'll be like one step the other, so stepped building, something like this. Okay, so accordingly we are going to take a normal building. Right now the height may be around 9 meter, and let's take D to be around 6 meter. So let's do the math right now. So it is like 0.09 into h is what? H we have taken 9 meter divided by root of D. What is D right now? 6. I get it around 0.33. So if I'm getting it 0.3, if I'm getting it 0.3, if I'm getting it 0.3, that means that it is less than 0.4. Correct? In that case, we can say that because it is more than less than 0.4, we are going to follow this method. Understood? I think now we guys have understood how it works. Why are we going to choose this method, not this method? So once we have understood that, we need to start finding the lateral force acting. So for that, you guys need to know this formula, AH. See, what is AH is? It is the desired horizontal seismic coefficient, AH. So normally for a structure, if you want to try to minimize AH, AH is something like if you want to find VB, that is lateral force, AH into W should be done. W is the live load, dead load, all those that I've discussed, that is mass. That I'll come up with that. But right now, you guys need to understand to find AH, that is the seismic coefficient, we need to know the zone factor. We need to know the SA by G and R by L. SA by G depends on the TA that we have found. See, right now we got 0.3 is the T. And if it is a rocky hard salt strata, we are going to follow this. And if it is medium stiff soil, it is this. And when the soft soil is given, we are going to follow this. How are we going to know this? Which one is the soil? We will be getting the after the SPT test, soil penetration test. We will be getting a report, and they'll be mentioning out what kind of soil it is, or even by visualization. If you are well, experienced, you can understand that too. So not a problem. So we have found SA by G right now. SA by G, it is now 0.3. That is less than 0.4 and more than 0. So that means we are going to take this 2.5. So that is the reason here we got SA by G. So that depends on soil condition and even the T time of oscillation. Okay. Once we got that, then comes zone factor. Zone factor depends on the area where it is. So normally what happens, there are four types. Before they should be five types. That is, even zone one was there. But right now they have considered to be only four of them. Zone 2, 3, 4, 5. And what happens is zone 1, where do we get that from? This is from the map. And zone 5, whatever they have mentioned, that is a very dangerous seismic zone area. So this is a very high seismic zone area, and we should be very, extra careful whenever we're going to design this area. So this is how it is. This is zone 2, and whatever you see green in here, that is zone 3, and whatever yellowish you guys can see in here. So Kerala can be taken to be 0.16, and zone 2, that is 0.10, that is Karnataka area, all those things. Okay. So now we have understood what is seismic zone factor. That is, let's take it at 0.10, and we got that. Now it comes to time for reduction factor. What is reduction factor? Reduction factor is something, if the material, the building is very good, very, heavier, and it has a strength, it has good strength, all those things matters. If that is there, the reduction factor will be more. Correct. That is like something we can tell that we can say something like this. Uh, R is something, that reduction factor is something. It is like strength of the material, building. So now let's go to this, understand that out. So there are four types in that, five types in that. We'll not go to this. Dual system is something different. Slab is something different. Structure wall system, we are not going with that. Brace also, we are not going. We are going with movement frame system. There is something that you guys need to understand when it comes to this. Here, you guys can see here MRF, M, sorry, OMRF, SMRF. So in the steel, we are not going with it. We'll go with RC buildings because we are talking about that. What is ordinary and special movement resisting frames? Special movement resisting frames are different, like the materials are the same. All the same, like OMRF, but there are special structures in it. Or special movement resisting frames, or maybe there is a floating columns or any kind of a structure, something like that. There, the reduction factor will be more. Okay, and the strength will be more. In that sense, only then we are going to use this reduction factor. But remember one thing, when I mentioned floating column, we usually will not be designing floating column when, I mean, we will not be using floating column when there is a seismic zone areas, the high seismic zone areas, that is zone 5, something like zone 5 zone. It is not recommended. It is there mentioned in ductile designing code book. Yeah, we'll not go to that now. So we understood what is R. So when the R is more, the AH will decrease. Good, understood. But there is other factor that comes to picture, that is I. If the important factor is high, if the important factor is high, in that sense the AH will decrease. Sorry, it will increase. So it is vice versa. R increases, AH decreases. If I increases, AH increases. So that is how it works. So importance factor, how do we choose that importance factor is? It depends on what kind of building is it. Is it a residential or commercial building, or is it all other building, or is it a government buildings, or anything very important where we public public presence is more, something like that. So we found all these things now. Now, as far as we know that AH is equal to Z by 2 into SA by G divided by R by I, importance factor. So this is the formula. Once we find AH, we multiply that with W. Now W, what is W? What is W? W is mass. How do I find mass? Mass is like if I take a live load and if I take wind load and sorry, not a wind load, sorry. If I take a live load, if I take a self weight load, and if I take lead load, I get this. But there is some clause that you guys need to know this. It says that, and always remember, whenever you're going to design in structure, it's better that you design it such a way that you take a live load of 3 kilo, less than 3 kilonewton in one case, and more than 3 kilonewton in one case, and in roof load you take it in a different SI. So 3 different live loads. Why? Because roof need not be considered imposed load, that is live load need not to be considered when there is a roof. Okay, understood. And I mean there is no, what is a reduction factor. And when there is imposed load to be considered, when should we consider it? When up to and including 3 kilonewton, we should take it to be 25%. 25% decrease in the load needs to be done when there is load that is below 3 kilonewton and 3 kilonewton, and if it's more than 3 kilonewton we can take 50% reduction. So this is how we do it. So once we found that, once we calculate, so what happens once we understood this, what we do, we calculate live load, then we calculate dead load, we add all those things. In live load there is 25%, that is maybe 3 kilonewton. So that means 25% into 3, that is 0.75. So 0.75 should be considered. Okay, then plus dead load and superimposed load, all those things. So something like that you guys need to do it, and we find VB. So VB, that is VB depends upon weight and age. So once we find that, we need to, yeah, understand what is diaphragm. Sorry, before that, you should understand what is this. So usually what happens, the load, if you get it in lateral force, lateral force, I mean lateral forces that we get for each force depends on this. We take summation of all the things. So what happens? For this floor, the yeah, we get it here something like this, and we get it here something like this. One, two, sorry, two, so three, two, and one. We add all these, we get summation. Okay. Once we get this summation, we use it here, and for single story, we use it here, and we multiply with VB, and we find QI. This is the thing that we need. That is design, lateral force, and force floor, this floor. And if you want to find for the second floor, we need to multiply VB with this floor. That will get it here. And same way, this. So all the flows will be done. So once we find that out, once we find what is the acting thing, what the force acting, we should know what is diaphragm. Diaphragm is something. For that, you guys need to understand three kinds of diaphragms. So usually what happens, I mean, usually in the, no, there are three diaphragms: rigid, semi-rigid, and flexible. So rigid is something like, so imagine this is a frame structure and the load is acting. Okay, there will be small deformation. That's it, small deformation. So that is the reason it will be slab is very stiff. And usually what happens, the slab is very, it will have more depth. Correct, correct. It will have more depth and more depth, and it will be connected. The load will be distributed easily. So this is how it works. Semi-rigid is a combination of flexible and rigid. So flexible is something. So usually what happens, you guys don't know that the load will distribute by this method. Load distribution is like this, tributary area method. Correct. And the load will be transferred to the bottom. Correct. The load will be transferred to the bottom. This is how it works. And here in this case, the load will not be transferred. Too much will not be transferred. A little amount will be transferred to the bottom. That is how it works. Rigid frames. And in this case, what happens is the movement is somewhere large because it is flexible. Correct. So what happens? The load will be like this. If the load it will be like this. Okay. So this is a rigid frame and the deformation is large and is in plane deformation. In plane deformation. In plane deformation. So here it is like, because it is rigid, it is in plane translation. Translation. So because it is rigid diaphragm. So force transfer is by through based on element stiffness. This element stiffness matters, and due to that, the load will be transferred. So this is how it works. And in this case, it is flexible, and due to that, force is transferred within, I mean, will happen based on the tributary area, these tributary areas, and area of the diaphragm is through this, because of this. Okay, so now you should understand in softwares like in ETABS, flexible diaphragms is followed. But normally tin shells, we take a slab to be tin shell, right? So that is how it is followed. So now you have understood, yeah, now we have understood what is diaphragm. Diaphragm is something like you take the whole load to one area, this one area, and due to the load acting, sorry, yeah, due to the load acting, there will be an action in the support. Just imagine this to be a beam and the load is acting and the deformation will like this, correct? How will the load distribute to the horizontal member? That is called as diaphragm. I think now it's clear for you guys. Understood? So diaphragm is something that helps you to distribute the load to the horizontal. In the building whose floor diaphragm cannot provide rigid horizontal diaphragm action in their own plane, design story shear shall be distributed to the various vertical element of lateral force resisting system, considering in-plane flexibility of the diaphragms. So this is they are explaining about rigid horizontal diaphragm. And in here they have mentioned considering to be flexible. That is, flow diagram shall be considered to be flexible if the deformation such that the maximum lateral displacement measured from the chord of the deformed member shape, this one, at any point of diaphragm is more than 1.2. This that is a formula they have given here. Understood? So this is how it is going to work. So once you have understood all these terms, once you guys have understood, I think they have covered everything now. Once you guys have understood all these terms, you guys can easily design this in ETABS. In the upcoming classes, I'll be I'll be explaining you guys how to design all these out in ETABS, and it'll be quite easy for you guys once you understand this. So if you guys like the video, please do share and subscribe.